Hi, I'm Nick. This is Upside Down Ideas 2022 YouTube channel. This is the first video on the channel, so introduction would make sense, but we'll leave that for another time, because now I want to share an idea with you I had nearly about a year ago. It's not about perpetual motion or free energy made out of nothing. It's an idea about how we could possibly get energy from the surrounding environment and channel it and use it for essentially free. I haven't come across such an idea before, and if it is the first place this is proposed, I would like everybody to be able to explore it freely. I want it to be completely open source, so please study the diagrams while I'm talking and take screenshots, pass them around if you like the idea. Let's have fun. Now, about the idea. It's a two-part system, with one part being heat pump. It could be any type of heat pump, ground source, air source, it doesn't matter really, as long as it has a high coefficient of performance. I will give an example for air source heat pump because I believe that's the easiest system to set up, but as I said, it doesn't matter what type, as long as the coefficient of performance, the COP, is relatively high. And what COP is, if you don't know, it's essentially you feed a certain amount of electrical energy into a heat pump. It uses that electrical energy to extract as much as possible thermal energy from the surrounding environment and make it available at point of use. For example, if you input 1 kilowatt of electrical energy and you receive 4 kilowatts of thermal energy, the heat pump will have COP 4. And that's what I'm going to give an example with, because I believe that's an achievable high-end heat pump, air source heat pump coefficient of performance, but there have been claims for higher, COP 5, even 6. I'll stick to 4, being a little bit more conservative. The other part of the system is thermal to electrical conversion device, and it could be various devices, Peltier device, external combustion engines like steam engines if it was high temperature input, or Stirling engine, which has the potential to work at lower thermal thermal input, like temperature wise. How it does work is on the difference between the input temperature and the cooling side. So you've got two parts of the Stirling engine, so that's what I'm going to use for the example. But again, as long as whatever device is used to convert the thermal energy into electrical has high enough coefficient of efficiency, the system can be made work. I'll give an example with Stirling engine with coefficient of efficiency of about 30%, converting thermal to electrical energy, because I believe that is achievable and almost available on the market, almost, because there are little Stirling engines incorporated as part of gas boilers, which give heat and electricity, heat and power boilers, and what I have seen claimed for them is efficiency coefficient of 36. I'll go for 30% efficiency of conversion thermal to electrical because it seems more achievable, and obviously there will be need of some exploration, play, adjustments, etc., because the boiler works at much higher temperatures, hundreds of degrees Celsius, while the heat pump's output temperature is only about 50-60 degrees. So the temperature differential between hot and cold plate, or part of the Stirling engine, will be much lower. But it's achievable, I believe, because the way you deal with it is you increase the transfer rate of thermal energy by increasing the size of the conversion transfer plate. I mean, on the internet you can find example small kind of toy devices which can work from the heat of your palm, Stirling engines. Obviously they're not anywhere near as efficient as they need to be, but it's possible. So back to the system, back to the idea. Let's say in the example provided in the diagram, you take 1 kilowatt of electrical energy, run it through a heat pump with COP, coefficient of performance 4, which means that it gives, for that 1 kilowatt of electrical energy, you receive 4 kilowatts of thermal energy. Now you take that thermal energy and move it inside the house, a dwelling, whatever, and run it through a Stirling engine system, which has coefficient of efficiency about 30% of converting the thermal to electrical energy. Now you have 1.2 kilowatts electrical energy and 2.8 kilowatts thermal energy, which is lost in the process. But essentially, since it's inside of the dwelling, it's not lost. It's heat released inside the house, the building, and it can be used for heating. The electrical energy, on the other hand, 1 kilowatt of the 1.2 kilowatts, which have been converted back to electricity from the thermal energy input, goes back to the heat pump to complete the process, loop it in, so makes it perpetual or continuous, self-perpetuating. The other 0.2 kilowatts are used either directly as electrical energy or stored or whatever. So that's it. I mean, even if the system doesn't quite work at that high percentages, if let's say you can't achieve 1.2 kilowatts, you can't achieve anywhere around 1 kilowatt for 1 kilowatt input into the heat pump, will be great. Even if it is slightly less, let's say you need to top up 50 watts, 100 watts. If you need to top up 100 watts to receive 4 kilowatts of thermal energy, that's the equivalent of COP of 1 to 40. Sorry, 40, because you're putting 100 watts of electrical energy into the system, topping it up externally, not from the system, and you're receiving 4 kilowatts of thermal energy. Okay, I'm lying actually, it's not COP 40, it will be COP 31, because out of that you're basically getting 3.1 kilowatts of thermal energy unutilized by the system into the thermal to electrical conversion, etc. So in any case, it's not the end of the world. You can achieve a much higher COP for the overall system. Ideally, you want it to be above 1 kilowatt of electrical energy conversion at the end of the conversion, thermal to electrical conversion, so you can get the system going without external input. That's it. It's as simple as that. Most of the components are actually available off the shelf, except for, as I said, the Stirling engine. We will need a little bit of tweaking and work and research and failures, etc. But I believe it's doable. I think it's doable. I believe it's doable, and I'll give it a go when I have the time and resources. And I want you to do the same. The more people try, the better chance of success. Now, about 9 months ago, I met with a guy who I was hoping could be interested to help me to popularize the idea and possibly build a prototype. I didn't get that help, but he asked a couple of questions, or some questions, and given the stage of the idea, the development of the idea, I thought it's a bit premature, but then I thought a little bit further, and here we are. One of the questions was how much such a device would cost, and I believe, based on the components which are available currently on the market, a price of about 5 to 10,000 pounds as per end of 2022 wouldn't be unachievable. Now, going a little bit further, what is the business case? What is the repayment period? Now, okay, based on the information which is available, which I could find on the internet, as far as energy usage, average house energy uses is concerned, apparently in UK the average use per household of gas energy is about 20,000 kilowatt hours per year, which if you use heat pump, it will, with COP4, it will equate to about 5,000 kilowatts of electrical energy per year. And additionally to that, the average household uses about 3,500 kilowatt hours of electrical energy for various uses. So that gives us about 8.5 thousand kilowatt hours per year per household, and with the current price of electricity per kilowatt hour at the end of 2022 being on average 58 pence per kilowatt hour, that gives average electrical bill, if electricity was used solely for heating and electricity use, of 4,930 pounds per year per household. Very similar figure, slightly higher actually, is achieved if gas is used instead of the heat pump with COP4. Now, in UK, there are about 25 million households, and obviously at just short of 5,000 pounds per year bill, 4,930 pounds per year, that equates to a saving, if the system can be made work and utilized country-wise in UK, of 123 billion 250 million pounds per year for the whole country, and individually per the households. Obviously, if the price of the unit is about 10,000 pounds, that gives a repayment period of about 2 years. I think it's well worth investigating. Now, going a little bit further and looking into the environmental benefits of utilizing such system, if it's possible to develop it, just very, very basic CO2 emissions calculations gives the following. To generate 1 kilowatt hour of thermal energy from burning gas emits 0.185 kilograms of CO2 in the air, and to produce 1 kilowatt hour of electricity produced by burning coal in power stations emits 0.94 kilograms of CO2 per kilowatt hour electricity produced. Now, based on the previous figure, and looking this time at the 3,500 kilowatt hours of electricity used per household, and multiplying it by the 0.94 kilograms of CO2 emitted per kilowatt hour, we arrive at 3,290 kilograms of CO2 emitted per household for the production of the electricity it uses. And if we go for the slightly lower CO2 emissions for gas burning, and we have 20,000 kilowatt hours per year average household usage, 20,000 times 0.185 kilograms of CO2 per kilowatt hour equates to another 3,700 kilograms of CO2 per household per year. So the joint emissions should be in the region of 6,990 kilograms of CO2 per household per year. That varies from the figures, the official figures from the UK government, of 2.7 tons of CO2 emitted per household per year, generated by household per year. Which I don't know why it is different. Maybe there is accounting for renewable energy sources, maybe there is some sort of offset from growing plants. I don't know, I really don't know. But let's go for the slightly lower figure of 2.7 tons per household per year. Again, we have 25 million households approximately in UK. And when you multiply 2.7 tons times 25 million, we arrive at 67,500,000 tons annual output per year, which actually is about 1/5 of all of the CO2 emissions based on 2020 figures for UK. Which was 326 million tons. Now, if we can save that, that alone is a good enough reason to do a bit more research and develop this system if possible. All of this is only in UK, just in UK. What about the rest of the world? Now, what's next? Well, I'll give it a go, and since I believe it's the first place such an idea, such a system has been proposed, I want it to be open source. If it is the case, please, you give it a go as well. The more people work on it, the better chance of success. If you like the idea, please click like, please subscribe. That will help the channel to develop and hopefully will allow me to spend more time dedicated to the channel, to the ideas, discussing it. There are other things to come. If you really like the ideas, if you really like what we're talking about, you can sponsor directly in the links below once I work out how that works anyway, which will be great help again. Whatever I come up with will be available freely to all of you, so there is no hidden footages for subscribers only, etc. There is no extra benefits. It will be just purely to help me and the channel to move on and develop. But please, give it a go as well. I think we all can benefit from developing such ideas, and that's how it should be. That's the only hope we have.